And you can think of the fixed points there as being the nice things corresponding to the concept of closure. But you can also think of this in topological ways, and what you'll get in the notation of the lambda calculus is all continuous functions from one lattice to the other. Now next door there, I think Spivak is talking about categories in general. This family of closure operators is a very rich category in itself. The closure operators can give you topological spaces in terms of their fixed point sets. You can think of continuity there. And so just as in general topology, topological spaces and continuous functions form interesting category. So we have a very interesting category of closure operators this way. And let me show you, before we take our break, something we can do with that. But, yes?
When you say closed, you mean closed in the topological sense?
No, I mean closed in terms of the operations that C is doing. C is taking input and munching it up there until it's like the thing of a group. A group could be a very large thing. Think of all Euclidean transformations of the plane. Okay? But if you just take a finite number of transformations and close it under the group operations, then you get just very restricted subgroups that correspond to certain geometric patterns.
Okay, so it's
right?
A restriction rather than,
Yeah.
It's not a closed set.
Yeah. But what it means is when you're done by doing those restrictions, there's nothing more to do. That's what closure means. So that's like taking the subgroup generated by a subset of the groups. After you do the group operations over and over again, you don't have to do anything more. It's already closed under the operation. So there are two uses of closed here. Closed for C is just fixed points. A fixed point is something that can't be fixed up anymore by C. It's already fixed. Okay? But now there's a second meaning of closed. The totality of fixed points of C form a topological space. In fact, it's a subspace of the power set of n with a power set of n topology. In other words, it's a restriction on the topology of the power set of n to a topology on a sublattice. Okay? And those topological spaces can be put together in a category. Different closure operators give you different subspaces, and the continuous mappings between the subspaces can be explained entirely in terms of our lambda calculus. And so this gives you a very easy way to see easy. Easy is in the eye of the beholder, but I say it took pretty elementary means to think of some fairly complicated spaces here and the category of spaces that are similar here by using the lambda calculus to give me the continuous mappings. Okay? Question?
My question is more math focused in the sense.
You have to speak louder, please.
My question is more math focused in the sense that given that functions are continuous to be able to establish computability.
No, say again.
Like for a function to be computable, it has to be continuous.
Yes.
But could you give an example of a function which is continuous but is not computable?
Sure. Because okay, so you could do it this way in terms of closure operators. This way, a closure operator which has a which is given by a recursively enumerable lookup table, is forming a computable closure there. When the lookup table is recursively enumerable, then I'm saying that this is computable. But now, if you were a magician, you could have an oracle where you keep adding something to the lookup table by asking the oracle leading questions. And you could do that in a very arbitrary way, and so the original closure would only get you a certain distance, but if you invoke the oracle, you get much more out of it. You know, like winning at roulette or something like that. What is going to be the next fall of the wheel? If you can answer that question, you get lots more money out of it, okay? The oracle could be very non-computable because it's godlike in character, okay? And so you would get a continuous function because it was based on only finite amount of information, but the oracle was giving you an edge over the honest way of playing the game. And so you could, if the oracle is extremely clever, you get non-computable things. Now, the last thing before we break is something we can do with this. Okay, is everybody more or less okay with saying the closure operators form a category, and the category is all notatable within our lambda calculus here in this model? Okay, can I go on? So this is the last step today. Mm-hmm.
Is there a connection with Charlie Collar correspondence?
Next session. Next session. Not today. I mean, not this moment, before the break at 3. But if you come back for the third session, I'll answer that question. Now, closures can be combined to give more complicated closures, and you can think of it in terms of topological spaces. If the fixed points of a closure operator form a topological space, and you take another one, so you have another space, wouldn't you want to form the product of those two spaces? Mathematicians are forming products of spaces every day, aren't they? Okay? So we can notate this in the lambda calculus very easily here by invoking some other enumeration operators. You see, it turns out that the full space power set of n, the full space power set of n as a topological space is homeomorphic to the power set of n times the power set of n. The space doesn't have any dimension. The real numbers don't satisfy that because r cross r is 2-dimensional and r is 1-dimensional. But the power set with the easier topology here is identical with its Cartesian square because sets of integers can be paired. I can say a pair of two sets of integers means put a copy of x on the evens and put a copy of y on the odds. Any pair of sets reduces to one set this way, and that single set can be decoded into the first and second terms there. Those are computable enumeration operators. Don't ask me how to write them in the computable lambda calculus. I could do it with a little arithmetic, but not today. Anyway, those are nice computable enumeration operators. And so now we can give a closure operator that works on pairs in the following way. If I want to pair the fixed points of C with the fixed points of D, what I do is take an input and regard it as a pair of two sets of integers. I make a D out of the second one, and I make a C out of the first one, and then I take the pair. So again, it's an elementary exercise to show by this definition that the product of two closure operators is a closure operator. It just means the first closure operator is doing all its work on the evens, and the second one is doing all its work on the odds. And so we paired them together that way. And in terms of the category, that is the pairing of the category. Spivak would tell you how abstractly to say that this is a categorical pairing operation. Now the last point is we can take fixed points. So let's begin with any closure operator whatsoever. And since pairing, as the bottom of the slide there, is written in lambda calculus with the benefit of lambdas, applications, and arithmetic, it's a computable continuous operator. So I can take fixed points of continuous operators. You have to be just a little bit careful here. I'm sloughing over a small point here to make sure after you take the fixed points you have a closure operator, but take my word for it. So begin with a closure operator A. Now do a fixed point equation because the combo B cross A cross B is a continuous function of B. Every continuous function has a least fixed point. Define B as the least fixed point. A is held fixed there. A is given. But now the cross operation is an operator. All our operators have fixed points. So take the least fixed point of B cross A cross B. Why would I do that? Well, if I take C just as defined as A cross B, then we can do a lot of calculation here. And A cross B. C cross C equals A cross B, since B is defined. Now, don't let your algebra get away from you here. You see it's associated to the right. So we don't get an identity. What we get is an isomorphism of spaces. C cross C is here. C cross C is, let me say it the right way here. Oh, no, I said it, I'm sorry I said it the wrong way. I jumped the gun here. This is wrong. This is not an identity here. This is a combination of spaces, but a general principle of categories is that the product in a category is associative, but it's associative up to isomorphism. So if I associate like this, and now I have C cross C. Why am I'm doing something wrong here. Uh-oh. I didn't give myself enough blackboard room here. Okay. Okay. I'm getting overtired. I have an identity here according to the definitions that this is A cross B cross A cross B, because by definition, B was that way. Okay? And now I don't have an identity here. I have an isomorphism in the category of topological spaces with products here to A cross B. Reassociation is not an identical space, it's a homeomorphic space in the category of spaces. So this is a isomorphism or homeomorphism in the spaces. But this is equal to C cross C. So the power set of n, using my Gödel numbering, is identical to its own square. But here the C that I've created by using least fixed points is only homeomorphic to its square. So that's good enough. Now what can we do with that? The next step is to define D by means of a fixed point thing there. Okay? First I'll prove that I already proved this isomorphism here. I'll now use this isomorphism to prove this isomorphism. And then I'll use this isomorphism to prove this isomorphism. And then I'll need some coffee. Okay. Does everyone see the isomorphism, how I set it up to get C isomorphic to C cross C? Okay, and so this gives me a lot of latitude for finding things that look like they're squares. But now I use some more category theory because I define D as a fixed point, and the function space is defined entirely in terms of lambda calculus there as it was on the other slide. Let's define D as the least fixed point there. So what happens here is if I take D cross D, that will be equal to function space D arrow C cross the function space D arrow C. Now I want to invoke the immortal name of Haskell Curry. Currying means a pair of functions can always be thought of as a function of two variables. I mean, a function of pairs. A pair of function can always be thought of as a function taking on pairs of values. So, as an isomorphism of category theory, this is isomorphic to D arrows C cross C. If I have the same input here, but two different output things here, this is always isomorphic of the same input to the cross of the outputs there. That's a general principle from category theory.
Is this not just a property of a product instead of parity? Isn't it just a
Yeah, I'm going to use, you're right. This is product because it's on the left hand of the arrow, okay? This is just product. Now I can use currying, okay? In a minute here. I'm sorry, I got ahead of myself here. But we know that C cross C is homeomorphic to C. So I get that. But D arrow C was by definition equal to D. And so that's the proof. It's not by currying. I'll use currying in a minute here. That's the proof that D is the same as its square. Question?
One more question. I cannot imagine how D can exist in this with this definition. How does it function, right?
Well,
The thing on the right is kind of too big.
oh, I'm very angry with you because I told you over and over again here, you see, that the notion of mapping can be written in lambda calculus, and so therefore the maps Maybe I didn't say it enough. Okay, I'm sorry I insulted you. I'll take it back. Once you see the lambda calculus for being a mapping, you can then form the closure operators of all those maps. Okay, so I needed to make one more step there. So, thank you. I was getting ahead of myself here because I didn't read the bottom of the slide. Once you see in lambda calculus what it means to be a mapping, you can say, oh, let's take all those coercions that take an arbitrary f and restrict its attention to the fixed points of C and only give as outputs fixed points of D. Let's take that contraction of the f's. That closure operator stands for the function space. We're going from the particular functions to all the possible functions. And I should have said that. Is that better? Another question? Okay. I'm sorry I missed over that. I was just getting tired, that's all. But now we can finish up this last part here, because now I can invoke Curry. Because D cross D is by this chain of isomorphisms, isomorphic, homeomorphic to D, then when I take D arrows D as a closure operator representing a function space, I rewrite this. It's an equality of D arrows C, because D was defined as being equal to that fixed point. D was being equal to that fixed point. Now it's time to curry. A function of one argument which produces a function of another argument can just as well be regarded as a function of two arguments. And so therefore, by something that we can validate by category theory, this is homeomorphic to D cross D. I can pull these things together by currying and do that. But now I already proved that this is isomorphic to D, and by definition, that's equal to D. So what I construct in this way by fixed points and following through isomorphisms is that there exists a non-trivial closure operator which is homeomorphic to its own function space. Topological spaces that are homeomorphic to their own continuous function spaces are topological models of lambda calculus, where every element can uniquely be considered as a function. And so that's the eta rule. And I did it in such a way that an arbitrary A was built into this, so we'll know that D is non-trivial space. Okay? And so that's a way in which you can justify eta by filtering out here slowly and tracing things there so that every element of D, every closed element of D can uniquely be thought of as a continuous function from the closed elements of D to the closed elements of D. And since everything is continuous there, the lambda calculus is verified. So that's before I had a consistency proof for alpha beta, because power set of n is a model for alpha and beta, and it's a non-trivial model. K is different from S. If you look at K and S and think of, in terms of the lookup tables, what the hell you would put into the lookup tables there, completely different sets. So that's a consistency proof for alpha beta lambda calculus. And now we have a consistency proof for alpha beta eta lambda calculus out of this. Thank you. for now. Back in half an hour. What I'm doing in the last section there, this is type-free lambda calculus and the category of closure operators, which is a very broad category, and you see there are lots of isomorphisms to think of in this category. But there's a bigger category that gets to dependent type theory. Do we have the strength today to get to dependent type theory? Some of you do. Let me at the coffee. Be here at past. I'm running to the coffee. There was an awful lot in the last session which I didn't prove. I think the outline that we have a model for the lambda calculus is pretty much there in the notes. What I didn't do is to say, taking advantage of the least fixed point theorem, that we get all the recursive functions we need. You have to go back to the definition of primitive recursion. You have to go back to the way recursively enumerable is defined in terms of primitive recursion, and see that you can redo that in the lambda calculus. So I didn't have time to do that. Then when I started talking about the closure operators, I was able to justify some of the things there. Some of it is just simple-minded lambda calculus checking out the formulas. But there's some more to check there, namely that the fixed points of a closure operator form a subspace of the power set of n, and that the continuous functions between those power spaces, those subspaces given by closure operators, the continuous functions between them can all be given by our enumeration operators. So there's something that needs to be checked out there. And then, of course, when I told you that the closure operators form a category, the fact that they form a category is just lambda calculus. But the fact that that category has products and function spaces, the definitions are very easy, but you need some proof that what I defined actually works in category theory as a product and works as a function space. So the closure operators, which correspond to the countably based algebraic lattices and continuous functions, the closure operators form a Cartesian closed category. When you say Cartesian closed category, there's no comma in between there. It's a closed category, meaning it has function spaces, and it's Cartesian, meaning that it has products, and altogether the products and the function spaces behave nicely. That was the currying argument that I gave there. Stuff has to be checked out to do that. But the point is, defining what you need to check out is right there in your lambda calculus, but you still have to check out that they have the right properties. And I did write out an awful lot of that in the papers that I give in the reference things. Oh, by the way, for the closure operators, I thought of some examples. Take the free group, that's a countable free group on 2, 3, 4, it doesn't matter, on a finite number, more than one generator. The free group is quite a complicated thing, and it's countable, and the lattice of subgroups of the free group is an outstanding example of an algebraic lattice. And via Gödel numbering, I could set that up inside of power set of n, because I can Gödel number the elements of the free group and then look at all the subgroups. Or take the free Boolean algebra. That's the Boolean algebra of propositional calculus. It has countably many generators because we use countably many propositional constants. And so the lattice of subalgebras of the free Boolean algebra is a nice example of an algebraic lattice. And again, via Gödel ring, you can put that all inside power set of n. So the closure operators give you an interesting example also that D can be equal to D arrows D up to isomorphism. It's quite a rich category, Cartesian closed category. But from the point of view of logic, it doesn't yet have enough structure on it. We have to put some more structure on there to get to what's called the Curry-Howard isomorphism between constructive reasoning and lambda calculus. So that's what I'm going to set up for you in the last section here now. So let's just review. We've got this topological space. We know what the continuous functions are, and we know what the computable functions are on that space, okay? And that we can do an awful lot via the enumeration operators. That's what we were trying to show first section. And that the power set is equal to its own square. Now, the disjoint union of power set plus power set is not equal to power set because that disjoint union really gives separated things, and the power set of n is not isomorphic to that. Nor is the power set of n isomorphic to its own function space. The function space via closure operators is a nice space, but the closure operator that gives the functions from power set of n is not homeomorphic to the identity function on power set of n. The two spaces, power set of n and its own function space, they're related, but they're not isomorphic. So we have to do more to show this. Now I missed out a piece of notation here because I copied these from other slides and I forgot to put the footnote in. Remember, to show that power set of n is its own square, I introduced those enumeration operators up there. Now, instead of writing pair of x of y, I'm going to write for short just x of y here. And so it doesn't really conflict with our original notation. The original notation was that the pair of two integers was like that. And if we take the, and this, I'm defining the pair of two sets there, and I'm going to use the same notation for it. But if I compare here and take two singletons, let's not get a confusion going here, as singleton subsets of the power set, the pair there is equal to the singleton of 2n. I put n on the evens and m on the odds. Wait, no, I'm sorry, not plus. I take the set consisting of two things, one even number and one odd number there. And so that's a pair of singletons is a set that's a pair there. So don't confuse those two things. But a more complicated Lisp-style notation is too much trouble there, so I'm using that as an abbreviation. Okay, now, what good are pairs? Well, it means if we have any subset of our universe, I can consider it as a binary relation just by thinking of which pairs of sets belong to it. Okay? You see, every set in the power set of n, every set in the power set of n is a pair of two sets. Okay? So every subset of the power set of n can be considered as a binary relation because we can just say, well, does the pair belong to the subspace here? Every A contained in the power set of n can just as well be thought of as a binary relation. Sometimes I think of them as subspaces, sometimes I think of them as relations, and I could consider relations between relations and things like that. There's a lot of feedback will come out because the power set of n is its own square. Okay, notationally there, are we okay? Now, what good are these binary relations? You see, power set of n is a juicy topological space, and it has lots of subspaces. And it turns out that the continuous functions between subspaces can always be achieved by an enumeration operator. So our lambda calculus is really helping us think of the category of subspaces of power set of n. But we can go a step further and think of quotients of subspaces. What does it mean to take a quotient of a set? It means you replace the element of a set by equivalence classes under some equivalence relation. Now, instead of using the equivalence classes, it's just as easy just to use the equivalence relation. We do that all the time. Sometimes the students don't understand it at all, but some professors say, before I do calculus, I better prove for you what the real numbers are. And so one definition of the real numbers is to take converging sequences of rational numbers and divide them up by saying there's an equivalence relation that says two sequences are converging to the same answer there. In other words, square root of 2 can be approximated in many different ways, and so the square root of 2 in itself can be thought of as an equivalence class of all those sequences of rational numbers that do in fact converge to the square root of 2. So those are called Cauchy sequences. So the real numbers are a quotient of sequences of rational numbers. Now, we can think of n as a subspace up to isomorphism here of the power set of n just by taking the singleton subsets there. But now we can also think of functions from n to n as being the functions in our universe there that make a singleton go to a singleton, some singleton there. Okay? And so ordinary number theoretic functions we can think of as forming a subspace of the power set of n, by thinking of those operators that take singletons to singletons. And so therefore, in the abbreviated notation here, n to the n can be thought of as a subspace of the power set of n. Okay? But now n to the n is all possible sequences of integers. I can interpret integers as rational numbers by reduced fractions and using ordered pairs and things like that. So I can think of all functions. In fact, I could enumerate the rational numbers one-to-one with the integers. So I could think of the sequences of rational numbers as being up to isomorphism subspace n to the n there. And now I can think of Cauchy sequences by means of an equivalence relation that will take those convergent sequences of rational numbers, and that forms the real numbers. So the real numbers can be considered as, by standard means that we even teach in the calculus, the real numbers can be thought of as a quotient of a subspace of power set of n. And what's even better with this model, the continuous functions from the reals to reals will come from our lambda calculus. We have plenty of continuous functions in our model there to even get all the continuous functions of analysis interpreted using a quotient of a subset of power set of n. Power set of n is already of the cardinality of the continuum. The subsets of power set of n are 2 to the continuum. And we're taking those equivalence relations as giving us quotients of those. So we haven't gone beyond 2 to the continuum here. We're not going to arbitrarily large cardinalities. But there's an awful lot of mathematics that can be done at that size. In other words, the structures can be of the size of the real numbers, and the structure you want to put on the subsets there are the subsets of power set of n that we're working with here. So let me show you how the logic of this works out. Now, for example, here I have a comment, I guess, better say. What I mean by a partial equivalence relation is just what in any course you would consider an equivalence relation is symmetric and transitive, okay? And the type that represents are the elements that are equivalent to themselves. We're only taking a portion of the elements of power set of n, so AX only happens part of the time. We're taking a quotient of a selection out of power set of n for it here. Now, for example, any subspace, which we could think of as getting its topology from power set of n here, could be thought of as an equivalence relation here just by taking the identity relation on the subspace there. So that's an easy example of an equivalence relation, the identity relation on a subset. Okay? But we can show that every possible countably based T0 space can be set up in this way. A T0 space means points of the space are uniquely determined by its neighborhoods. Countably based means you only need a countable number of neighborhoods overall to make all the distinctions necessary. And so there are lots and lots of spaces, like the real numbers, which have a countable basis, okay? But now we can make a continuous embedding of any such countably based T0 space there simply by indexing the neighborhoods. That's sort of like giving Gödel numbers to the neighborhoods. And then mapping any point of the abstract space to the set of indices of its neighborhoods. And the T0 axiom says, oh, that has to be a one-to-one mapping because every point is uniquely determined by its neighborhoods. So now you just have to check, when you have time, that that carries the topology over. In other words, no matter what topology you start with, if you make this passage to power set of n to a subspace of power set of n, the topology of that subspace that it inherits from power set of n is the topology you were looking at. And that was already proved when I was 4 years old by the Russian topologist. But there's also another thing that needs to be checked out there. You also need to check that when you make this embedding, that you can make sure that the continuous functions between these subspaces are all given by the enumeration operators. And it's also not a very long proof to do that, but today we don't have time. So this is another indication of the richness of power set of n as a topological space. And of course, we're analyzing the things with the help of our lambda calculus. So there are the closure operators we talked about. And so the closure operators could be considered this way too, just by taking the identity function on their fixed point set. And so you get the category of closure operators in here, embedded in the category of quotients of subspaces of a power set of n. But now we want to go further and say, I already know lots of good subspaces and even quotients of subspaces. What about the totality of these quotients? I'm now going to call these quotients types. Just like with the real numbers there, I have a certain amount of structure on power set of n, but when I take the equivalence class, I'm saying that's now my formal definition of the type of the real numbers. Okay, question?
Yes, I actually have a question about the previous slide.
Okay.
So it said that closure operation is uniquely defined by its range. So is there like some kind of constraints for this statement? I mean, double negation is not always defined by a range, so it should be well-founded or something like that. So
I don't think that comes into it, and be careful there, negation is not a monotone operator. We're only using monotone operators here. So here is the thing. Let me tell you here. A very good example from closure operators is the lattice of subgroups of a group. Okay? So the closure operator is to take an arbitrary set of elements and to close it under the group operations. Okay? Suppose we only know the subgroups. How do you determine closure there? Well, you say, take a set of elements and take the intersection of all subgroups containing it, and that will be the closure of it. So the fixed points of the closure operator determine the whole closure operator.
Yeah, we have a well-founded case. So if we don't have well-founded case, like, I don't know, just...
Well-foundedness, I don't think, comes into it. I'm sorry, I don't see...
So, so where does it come from? Like, is it so in a general case, general lattice?
Well...
No, lattice, okay, lattice, so there is a bottom.
No, the bottom thing doesn't come into it. The bottom thing comes in to defining least fixed point, and that would be related to closure operators, because if you want to define the subgroups there, you could think of the operator M that says, let's just take the products of the elements that we were given, okay, together with identity, say. Maybe let's take all, no, that's not a good example. The thing is, in making a closure, you can do a one-step closure by just doing, okay. Let's take only binary products and inverses in my group, okay? That's a one-step filling things together. I allow the identity element, I take the group product of two elements, and I take the inverse of a given element. So if I start with a set and only taking those binary products, it's not a subgroup. I have to do it a second time. So this operator M that just multiplies things together one step there, you have to take M of M of M of M of M of N. You have to get the least fixed, starting with X, you have to get the least fixed point over X there. And so that's where the closure operator comes in. And that's, so for example, like if the operator said, okay, by fiat, I'm going to give you all the green elements out of the thing there. Then, of course, if you start with the empty set, you then get the green elements. But now when the green elements are multiplied together, they may give red, blue, and what have you there. And so when you do M of M of M of M of N starting from the empty set, you get the least fixed point of that operator, and that will be the subgroup generated by the original green elements, okay? And so that's the relation between least fixed points and closure there. So they're very, you use least fixed points to define interesting closure operators there. But maybe I'm not answering your question.
Well, I believe we're still like in a kind of constrained area where basically in this latter there is this, it's well-founded. So I mean, if you go with subgroups like, okay, I will not go there.
No, I don't think well-foundedness comes into this part of the discussion. But of course, there are arguments that you need to show that it requires only finitely many steps in order to get to any one element, and well-foundedness will come in there. But I don't think it's in this part of the discussion now. Okay, so a type is just a partial equivalence relation. And like with the real numbers, there are an awful lot of types that we can think similar there, and all those algebraic lattices, all those closure operators, there are an awful lot of types there. And we can make a category of types there by looking at the enumeration operators that map equivalent elements to equivalent elements. Okay, so if I'm given two types, A and B, then I say enumeration operators are equivalent mappings between things of type A and things of type B, if and only if two equivalent elements of A end up as two equivalent elements of B. Now, A and B are reflexive and symmetric relations. That's what a partial equivalence relation is. Now, this formula is not symmetric. Is that relation from F to G, is that a symmetric relation? You need to do a little proof in first order logic. Most logic courses I find excruciatingly boring. You know, who cares whether two universal quantifiers commute or not? You knew they did anyway. Why do you have to give a proof of that? But now here I really have to use some quantifier manipulation to show that if F is related to G, then G is related to F. So you see what I do is I interchange A and X and Y in A, and I interchange G of Y and F of X in B, because both A and B are symmetric. And now I rewrite the bound variables Y as X and X as Y, and now it matches this definition here. See, I have to use a little predicate calculus to rewrite bound variables. And so if F is related to G, G is related to F. Small step in predicate calculus, but necessary here. What about transitivity? If f is related to g and g is related to h, why is f related to h? Anyone want to tell me the proof? Remember, if A has a symmetric and transitive relation, if x is related to y, then y is related to x by A, so therefore x is related to x. X is not related to x overall because it's only a partial equivalence relation. But on the things that are related by A, x is related to x. You see now, if f is related to g, I can take x equals y in that part there. And now when g is related to x, I can use transitivity of b to get f is related to h. Do you see the proof? It's a little bit of predicate calculus. Want me to do it again, like Professor Church said? I'll do it again.
Sure.
You didn't see it?
What?
The proof that it's transitive. If f is related to g and g is related to h, then I can piece the two things together and get f related to h. Did you see that proof? Have you taken a course in predicate calculus?
I have not.
Oh, darn. Maybe you should. Anybody object to what I suggested as a proof? Don't you see the proof? I'm absolutely willing to stop. It's only 4 o'clock. Okay, so you see you have to do a little bit of logic to make sure things are hanging together here. And it shouldn't be too scary. There. Okay? And so this allows us to not only see that the types form a category where we can say what it means for f being a mapping from A to B, but we also get the function space out of it here. Being a category means behaving well with respect to the equivalence relations, but once some functions behave well with respect to the equivalence relation, lots of functions do, and we have an equivalence relation between functions. So that's how we get to function spaces, from just a function behaving itself to knowing the relation of when two functions are behaving the same way with respect to the equivalence relation. Does that make sense? You see, that's how we go up the type. We're getting mappings between types, but the types have the space of all functions that map well. And sometimes you need to really check things out. The statement that two things are equivalent by A can be thought of as a very mini type there. It's just the equivalence relation on the equivalence class of X and Y. That's just a fragment of A there. Sometimes we'll need to use that type in expressing things here. And when you go back and look and see how subspaces which use identity relations on the subspace, we're expanding the category of subspaces and continuous functions to the category of types. Everything lives together in a happy family here. And there are plenty of continuous functions from power set of n to give you all the functions you need. Now let's do products and sums. Well, products should be very easy because we can just use our ordered pairs. So what does it mean if we take the product of two types there? We just take the equivalence relation between pairs such that the first terms are equivalent according to A, and the second terms are equivalent to B. And we should check, or I'll give it to you as homework, that in the category of types, this is the product in categorical terms. Shouldn't be surprising because pairs were behaving so well on power set of n. Why shouldn't the pairs behave well on partial equivalence relations? But you see, it's a higher level of abstraction here because the equivalence relations are sets of pairs, and we're going between pairs of pairs there in order to get A cross B. So we're moving to more structure as we compound these things here. But with the help of our lambda calculus, we can write out the proofs that the category is in fact giving us categorical products.